Okay, I'm going to do a brief introduction. I'm very happy today to have Jana Tumova from the KTH, Royal Institute of Technology. She is from the School of Electrical Engineering and Computer Science. She received her PhD in computer science from Masaryk University and had a postdoctoral fellowship in KTH. And then she liked it so much that even after she was a visiting researcher at MIT, Boston, and other places, she is now there as an associate professor. She does really cool stuff on using formal methods in decision-making, motion planning, and the control of autonomous systems. And she is a recipient of the prestigious Swedish Research Council starting grant to explore compositional planning for multi-agent systems under temporal logic goals, and also has I'm sure it's an acronym, WASP Expeditions project, focusing on the design of socially acceptable and correct by design autonomous systems. But this is just a bio. I just know that she does really cool stuff, and she's going to talk to us about her research today. We are very happy to have you here, Jana. Go ahead.
Thank you so much. Thanks so much for having me and letting me talk about some of my cool stuff. So I'm going to share my slides and yep, let's go ahead and get started. Okay, so I will be talking today about motion planning with temporal logic tasks and constraints. I understood that you guys have a computer science background, maybe you know a bit about robotics, so I will take it easy, but feel free to interrupt me anytime that you want and ask questions. I don't see chat though, so you have to, maybe Martin or Mohan, just jump in and
we will monitor the chat. If there is a question, we'll post. Yeah, go ahead.
Super. Yeah, thanks. Okay, so let's start with motion planning. Traditionally, motion planning, I'm sure that you know that this is about planning motion from some source to destination while avoiding obstacles. That's a topic that has been out there for a very, very long time, very well investigated topic. What I'm showing here is RT star sampling-based algorithm that is asymptotically the optimal, because I will be coming back to it quite a bit here. And let's just say that RT star takes a bunch of samples and gradually reconnects the tree that is being built around here, so that it becomes more and more shorter and shorter path from your source to destinations while avoiding obstacles. However, motion planning can come with more involved goals. You might be interested in saying more than just go from A to B. So for instance, you can be interested in autonomous driving, going from A to B, but you want to obey road rules as well. Or you can have some surveillance robots, and then it's not only about going from A to B, but patrolling some regions A, B, and C in this particular order, while never entering some region that is dangerous. Or you can think about an unknown space and you would like to map a room, but while you are doing this mapping, you would preferably like to stay within certain distances from the walls, from people, from obstacles, and so on, if that's possible. So now when we have these more involved goals, the question is, how do we make them happen with motion planning? And the answer is, one of the possible answers is we can use temporal logic to express such goals. And then we can use model checking principles to enforce such goals in motion planning algorithms. So temporal logic, just in case you have not seen this before or you need a refresher, this is temporal logic. It has a bunch of operators. Some of them are classical propositional operators like and or negation, that stuff you might know. But then we have these special temporal operators like until, next, eventually, and always. So this eventually operator essentially tells us reachability. So when I have a path or a trajectory of a robot, what I want to see is to see this pi happening at some point. Eventually, pi will happen. Then this globally or always operator, when I say globally, not pi, what I'm aiming for is not to see pi at all. And then I have sort of safety. And you can combine these operators in much more complex formulas like surveillance, always eventually pi will mean that you will keep seeing pi, so that's for the surveillance. Or you can sequence the goals. You can say, I want to keep seeing pi1 until I see pi2, until I see pi3, pi1, until pi2, until pi3. Or I can say that I want to see pi1, and sometimes after that I want to see pi2. Or I can even specify things like request response properties, where I say always, whenever I see a request, eventually I want to see a response. So this is a temporal logic called linear temporal logic. It's one of the basic ones. There is no involved specific time constraints. It just talks about ordering of the events. And with this logic coming from computer science, from formal methods, you can actually ask very easily, not very easily, but rather easily, you can ask, does my system satisfy this LTL property or not? And a tool called Model Checker will say yes or no. So you have Dave Parker over there in Birmingham. That's the person to talk about model checking, especially when it comes to probabilistic systems. So I talked about model checking as the procedure telling us, yes, a system satisfies an LTL formula or no. But model checking based planning can use these model checkers with a little bit of twist or a little bit bigger twist to ask a question: which of the plan's controllers ensure the satisfaction of the formula for an autonomous system or robot? So in the beginning, I have some sort of autonomous robot. I will model this system with its actions, with its control inputs. I will specify what I want from that system in my temporal logic. I will put these things into model checker, and this model checker tool with its algorithms will give me a plan. So that's in a nutshell what's going on in model checking based planning. This model checker tool can be based on different principles. One of them is automata-based model checking. When you take your temporal logic formula, you translate it into automata, and then you take your model and your automaton in the model checker, and you create a product automaton that contains the behavior that the system can do, and that is at the same time permitted by the formula. And then you do a graph analysis on this product, and that's how the plan or controller is computed, or how the model checking question is actually answered. So now I started talking about these models. Model checkers can work with deterministic transition system, non-deterministic transition system, deterministic time Markov chains, MDPs, timed automata, hybrid automata, and there are much more temporal logics than LTL. There is syntactically co-safe LTL, which is a more efficient finite fragment. There's probabilistic LTL, probabilistic CTL, branching logic. There's metric time logic. There is signal temporal logic. There are all these sort of logics that have different expressivity and different computational challenges associated with them. And there are different kind of models. Same thing, different kind of expressivity, but also different kind of computational challenges. Now, the thing is that our robots are hardly ever deterministic transition systems, all right? They are some kind of dynamical systems. They are governed by x dot equals, and they live in continuous world and continuous time. So before, if we want to control robots with this model checking based planning, the first thing we need to do is to discretize that model somehow by abstraction. So one way to discretize this is through these sampling-based motion planning algorithms. You build an RT star, and then you treat this RT star as sort of under approximation of your original system. Or you can build different kind of abstractions based on partitioning of the environment, and then looking at dynamics of the robot and say that here connecting region 1 with region 9 if you can actually control the robot to drive from region 1 to region 9. So this is an important step that I will not be talking too much about today, but it needs to be remembered that the question how you come from an autonomous robot to a system that can be handled by a model checker, that's a non-trivial question. All right, so that was the introduction. What we have now is that we have sort of a framework where I can take my robot, my LTL formula, and I get out a plan that provably satisfies the formula. In the first part here of the real content after the intro, I will focus on motion planning for autonomous vehicles with traffic rules. So here you have a vehicle. It starts in some kind of pickup location, and it wants to go into this outer intersection through this road segment. And there is also a construction zone happening, and the usual road rules according to Vienna Convention would say something like you should stay in the right lane. You should not enter the construction zone because there are these signs saying you shouldn't do that. You should keep the speed limit. You should not cross full lane if there is a full lane. You should not enter a sidewalk even if sometimes it seems like an option. So you have a bunch of these road rules, and what you can do is, well, we can express them maybe in LTL, right? We just talked about it, so why not? We will say whenever there is an assumption, there needs to be a guarantee until you reach the end of the segment. This is sort of reactive formula. Assumption implies guarantee until goal. So no matter what you do, this is true. You want to stay in the right lane. When you see a sign saying under construction, you should not enter a construction area. When you see a sign saying no overtake, you should not enter the left lane. When you see a sign saying 50 miles per hour limit, then you should keep moving under these 50 miles per hour. So this all sounds, legit, right? We can all do that. And then we can use a combination of a suitable motion planning approach, like RT star, build that nice tree, use the model checker, this automata-based strategy synthesis tool, and get a plan out of it and follow it in my RT star tree, and I'm all done. In principle, yes. But when we started looking into this problem a little bit closer, we realized that there we go. This is basically the outline. So when we started looking a little bit closer, we realized that sometimes, and very often actually, the set of traffic rules that you are given cannot be satisfied simultaneously. Like here, at the same time, you cannot stay in the right lane and avoid the construction area. So different road rules come with different priorities. They come with a natural disobedience. We as human drivers, when we are out there on the streets, we bend the rules. We sometimes violate them for a little while so that we don't come to a state where we say abort mission. There is nothing I can do. That's not what we do as drivers. Just find a way. So now we are getting essentially to the question, what happens if the set of traffic rules cannot be satisfied simultaneously? And then I do not want to get, there does not exist a plan. What I want to get is a little bit finer characterization of the plans, something that will tell me which plans are better and which plans are worse. So we came up with this quantitative evaluation of LTL formulas, quantitative semantics. So assume that you will have the transition system from the RT star or some abstraction. And when I take a path in that abstraction, in that transition system or RT star tree, I can measure level of unsafety of that path or trajectory. So I will measure it as the time duration associated with the transitions that need to be ignored, that happen but shouldn't have happened, in order to make the unsatisfied LTL formula weighted by the penalties. And this math here basically says exactly that. So we are just looking at what you shouldn't have done, but you did on your path. And then some paths come out as worse and some paths come out as better. And that's great because that gives us optimization function. And it turns out that this automata-based approach, this model checker, can be actually twisted to answer the question, which of the executions, paths, trajectories, call it what you want, violate the formulas the least, instead of satisfy the formula perfectly. So what we did there is we translated every single formula into finite automata. We were dealing with finite LTL then. We enhanced it with some weights. So these weights were carefully designed so that it reflects the level of violation. And then we did the product automaton, but in our case, it was weighted. We did the graph analysis, and in our case, we were not happy with an accepting run, but we were looking for the shortest accepting run, and then we can project it into the least violating plan. And we have a sequence of lemmas saying that this actually works. So what it means in practice for the autonomous driving is this. When I take a look at the classical RT star, I'm incrementally building a weighted tree. I'm incrementally updating the shortest path, and distance is my optimality criterion. So on this left-hand side, what you see is how the tree grows, how it's being reconnected, and how it slowly converges to the optimal path. Now, with least violating or maximally satisfying RT star, instead of building a weighted tree, we were building a weighted product automaton. So we took the formula, we translated it into this bookie, equipped it with weight, and then put it into the tree as another dimension, essentially. And we have a product automaton. Instead of updating the shortest path, we are incrementally updating the least violating path. And the level of violation is here the primary optimality criterion, and distance is our secondary optimality criterion. So what you can see happening in the video here is that when we do the RT star, the least violating, the car that is instructed to stay in the right lane, but not to hit an obstacle, will go by the obstacle quite closely, but after it's done passing it, it will return to its right lane. So this is not an algorithm that would do obstacle avoidance. It's no if then else, if you see an obstacle, go by the obstacle and then return to the right lane. This is all enforced by having the LTL formulas expressing the road rules and saying, synthesize the least violating plan for me. So already back in 2013, we were able to put this on an autonomous vehicle and the autonomous golf cart back then. You see here is basically the algorithm in action implemented by some of very smart people in Emilio Frazzoli's group. And you saw that the obstacle was passed by very closely, and then the car returned back to the left lane. In this case, it's left lane because we are in Singapore. Well, and since then, since 2013, we looked in a bunch of other things. We looked in some advanced settings like limited sensing and multi-vehicle settings, either collaborative or competitive when we have other drivers, and we try to do intention-aware motion planning. So, yeah. We followed up and developed it in a little bit more realistic setup. I would like to spend a few minutes on our ongoing work that is towards social acceptability, which is sort of exploratory project. So when we have all of these trajectories satisfying road rules or satisfying them as much as possible, we still have a question, which of these four trajectories is the right one? which one would you take? Would you take the one that really goes by the obstacle very closely, or would you go by a little bit wider trajectory? So now the thing is that this is also a question of personal preference. Some drivers would drive a little bit more aggressively, and some would drive a little bit more defensively. So the question is, can we actually encode driving styles of people using this temporal logic and then design a trajectory or motion plan that will actually reflect on the desired driving style that one wants to achieve? So here, LTL is not enough anymore, because LTL is, very discrete. There's a discrete sequence of actions, and we need to use signal temporal logic, STL, and some sort of parameterized quantitative semantics as the finer constraint preference specification language. And then what we did is also we evaluated whether these parameter calibrations leading to different trajectories actually led to different perception of driving styles. The answer is, of course, yes. Because, yeah. So STL, signal temporal logic, we have seen something like this before with LTL. Now we have here these intervals. So this says until, within interval A to B, eventually within interval A to B, and always within interval A to B, something needs to happen. And our atomic propositions are not true, false anymore, but they are comparisons of a function of a signal to 0. So, so it's not binary. It is still binary, of course, but it's not an atomic proposition that holds or doesn't hold. There is a continuous signal here that you compare to 0. So, so potentially there is many more values that can happen here in the left part. So now when we are interpreting STL, we are interpreting them over continuous signals, and I borrowed this picture from Alex Donze, one of the authors of the signal temporal logic, because it illustrates very nicely what the logic is about. So this formula is saying to us always between 2 and 6. So it can be read as whenever the time is between 2 and 6, the value of the signal should be below 2. And this is what's happening here. The green square represents the time between 2 and 6 seconds, and the absolute value of the signal is smaller than 2, and you can see that the formula holds. But you can also ask how well it actually holds. And you can see that, there is this left robustness here, 1.2 seconds, that you could have started asking for the formula to hold earlier and it would still hold. So there's robustness 1.2 left time robustness. And there is this tiny little robustness here in the values, where you see that it's actually maybe 1.9 or something. So there is 0.1 robustness. Your signal could go a little higher here. So this STL comes very naturally with a quantitative semantics called robustness of STL. And that's very nice when we will start talking about these trajectories. Turns out that you can encode road rules or different kind of rules of conduct on roads with STL. There are a couple of works that have done that. We have also tried to do it. And for instance, you can encode a 3-second rule in the responsibility sensitive safety model, which says that if I have 2 vehicles, one of them is ahead of the other one. The longitudinal distance between them is denoted as safe if the time that it takes to transverse is at least 3 seconds. So you can express this in an STL formula. And then, of course, the vehicles that will have 5 seconds between them will be evaluated as more robust than the vehicles that have those exact 3 seconds. And the vehicles having 2 seconds between them will be violating the rule, but they will be violating it less than vehicles that have just 1 second between them. And with this, basically, we figure out some parameterized quantitative semantics and alternative semantics to LTL. I'm not going to go into the details, just say that there are parameters that tell you how important it is for the STL formula to be satisfied versus how important it is that there is a time efficiency on your trajectories. So it sort of compromises the time efficiency and the satisfaction of spatial preferences that we view as preferences here, not as hard rules. So we basically, using this STL quantitative semantics, we generated a bunch of different trajectories and presented them as traffic scenarios in Carla. We asked people, what do they think, how defensive is this driver? And it turns out, so here is an example what's coming out of our parameterized automatic generation of trajectories. So in the defensive, you see that there are like large space between the vehicles. With the neutral, it's sort of midway, and with the aggressive, the car just goes. So these are generated with different parameters A and alpha in our evaluation. And what we ask people is, do you perceive this as defensive, neutral, or aggressive? And what we got out is that there is a correlation between what people perceive as aggressive, neutral, and defensive, and what we generated as aggressive, neutral, and defensive. And currently we are working on actually designing these trajectories with the desired aggressiveness level, so that we not only satisfy the road rules as much as we can, but we also perceive the behavior of the autonomous vehicle as good. It's perceived well by people who are around it. Okay, so that was on the autonomous driving. And I would like to continue just for a few more minutes on what else you can do with this STL constraints. So depending on how you parameterize, how you choose your parameters, you can end up having different kind of trajectories. So here you are starting in the bottom right corner. You have a temporal logic formula for your task that is saying that you want to visit the 2 gray squares in either whichever order, doesn't matter. And then we have STL formula that is telling us that we should stay within certain distances from obstacles. In the left-hand side, the parameters are chosen so that it's quite important to get that job done efficiently, and it's less important to stay within those distances from the obstacle. In the right-hand side, it's quite important that you stay within the prescribed distances from the obstacles, but it's fine if it takes longer. So this is what the A and alpha parameter choices do. What you can observe in the left picture here, when passing through the narrow passage, you're passing right in the middle. This is what the robustness does. This is where we are trying to be least violating. And it's similar here. We are trying to pass in the middle exactly, which is a side effect of trying to be least violating. So we can apply this to any moving robots, and we joined forces with exploration algorithms, with people who do exploration. And their problem was to basically fly an UAV in an unknown space and build a map. And, you know, AEP, or Autonomous Exploration Planner, the very original algorithm that comes from Patrick Gensfeld's group at RPL here at KTH, would look something like this. This is the first version, not very optimized. And it would just go around an empty room in some sort of, it's not even a pattern. So what we said is, let's, you know, put these STL formulas and let's require the vehicle to stay within certain distances from the walls, because walls are interesting. Walls are where we gather the information from the environment. And what happened is this. So this is what happened when we said we want to stay around the walls. And it just started to feel more organized, the whole exploration process. Indeed, what we did there is very similar to what we did in the least violating planning for autonomous vehicles. Again, we built a weighted tree. We were looking for least violating path in RT star tree. And this time our optimization function is some kind of cost function associated with the robustness of STL. And I'm going to show you a video from a lab that will compare next to each other the motion with vanilla autonomous exploration planner and with this STL constraints. And maybe I will just jump through it a little bit. What you can see is that a side effect of going by the walls is that you actually do finish the exploration faster, quite faster than when you just go greedily to the frontier of unknown and try to gather the information as much as possible. Well, yeah, so it was a little bit faster. The distance traveled was a little bit smaller, both in empty room and the real office. So we got a little bit more, little bit achievement there, in the sense that we made the exploration more efficient by constraining the motion with this temporal logic stuff. And the very last thing I would like to talk about is a little bit of advertisement of our newest RSS paper. So forget STL again. We're not going to look into constraints anymore, but we are going to go back to sort of having higher level tasks in LTL specifications. But we are still in unknown environments. So imagine that you have some office-like environment like this. What you would like to do is, in each room, visit the bin, the green thing, waste bin that is full. Your robot would like to go there and empty it. And it's an office-like environment, and it's unknown where the bins are. But as it usually is, often there is some structure to the environment. For instance, most of the people would have, I'm speculating, but I do have bin next to my table so that I can throw stuff easily. Some people like to have their bins next to the door because they can throw things out on the way out, and so on. But there are some patterns that keep repeating there. And we were wondering whether we can learn these patterns as we go and make sort of integrated exploration and motion planning that will be faster than doing exploration, finding out where the things are, and then doing motion planning with LTL specifications there. So what we proposed is something that we call semantic abstraction guided motion planning, where we have our property that is translated to automaton, and we have our system. This time we are using RG instead of RT star, but it's in principles it's similar thing. So we have RG graph, and then we built a semantic abstraction of the environment. We work with that semantic abstraction and the property automaton, and we are biasing the graph, the RG search, so that we are more likely to hit the areas where we are likely to find the bins. just to give you an idea what's happening inside is that when I have a robot and it visits this first bin, it realizes that it went through the area where there was a table. So this is this upper part, R1, it entered room 1, then it saw the table in room 1, and then it saw the bin in room 1. And this was seen in the RG graph. So what we do is we enhance the semantic abstraction of the space, and we say, okay, I saw this in room 1, maybe I will see a similar thing in room 2. And we put these maybe edges there. We are thinking, maybe there is a table in room 2 as well. And maybe there is a bin next to the table in room 2 as well. Very roughly, just to give you an idea what we are doing there. And if we look at our results, I think that the most important part is being said by the total length of the path. So first, if we explore everything, find out where the bins are, and then plan, what we do is that the exploration length would be something like 57 units. And then we still need to execute the plan, and we will take extra 20 units to do that. When we start doing things simultaneously, when we start exploring while planning while exploring, so when I see something interesting, I'm already trying to make progress to satisfy my formula, it gets a bit better. So I get to total length of the trajectory 56. But then when we start biasing the sampling of RG towards the region where we think that there is maybe something there, we get to 29. So there is some improvement achieved by learning where these things are. And yeah, if you want, check out our newest RSS paper. So to wrap up, some of the takeaways here are that temporal logics in motion planning bring in some expressivity, richness, and somewhat user-friendliness in terms of expressing complex missions. They are rigorous, and they come with this model checking procedure, which can give you provable guarantees. You can twist the model checking procedure so that you still get provable guarantees, but it might not be guarantees on 100% on perfect satisfaction. But with suitable quantitative semantics, you can end up having least violating or maximally satisfying motion plans. And with that, I also wish I had time to talk about more things that we are doing, the multi-robot planning and control, and especially dealing with complex dynamics, which is one of the topics that my brilliant student Puriyat Ashvar is working on. That's very exciting when you have a robot that you cannot just do RT star, because a small error in tracking that trajectory would cause a large error in reality. Then what do you do next? And he's working with data-driven approaches and safe motion primitives and so on. So that's very cool work that I did not have time to today. Well, thank you for listening, and thanks to my collaborators and my properly socially distanced group, of course. Thank you. I'm happy to answer any questions. And feel free to get in touch via email if you have some other.
Yeah, thank you very much for the brilliant talk. I really enjoyed it. So in case you have any questions, just feel free to either speak up or post them in the chat.
I think Iran said she had one, so let her go first and we'll give others a chance.
Yes, exactly.
Hello, thank you so much, and it was a great talk and impressive work. I truly enjoyed it. And I used to be in Sweden, so it just feels really, really
cool.
Weird when I'm listening to someone, but I was in KTH. Anyway, so I have a question. I have several questions, but I will ask one. The rest I will ask if there was time.
Sure.
my question is about the part that you explicitly said that you don't want to focus on that, and it was about the partitioning part. And so to me, partitioning cannot be fixed if we have dynamic obstacle. By dynamic obstacle, I don't mean people. For example, I mean when there is the obstacle would be created as a result of robot action, for example, a construction site, a bunch of pile just moved. So do you think, have you ever done something with that, with the dynamic partitioning, or what was your feeling or idea about what you've explained about, for example, weighted automata, which I didn't know about that before. Thanks for telling us that. So what do you think of that? I mean, did you think it's applicable, the stuff that you explained in the first part, to the dynamic type of partitioning? What are the challenges?
That's a really good question. I have not seen works that would focus on dynamic partitioning per se. I have seen talks that would focus on stuff like works that focus on stuff like I have assumption that my environment looks like this, but I don't really know. So as I go, I keep revealing that it's actually full of obstacles. And then what you need to do is either recompute everything from scratch, or these work focus actually on patching the things in the model checker. So when you have the self-partitioning and you have the formula and the automaton and you create this product, then either you can recompute everything, or if something small changes, you can kind of find a patch in the product from something that you knew was working to something that you know is working from then on. So people are taking a look into how to handle it efficiently like this. That's what I have seen. I don't have anything smarter, I'm afraid.
Sure, thank you so much. So I will go down for other people to ask.
Okay, who next? Okay, nobody's there, then I will get a chance too. I should have some superpowers, someplace at least. Okay, so a couple of questions. So like when you have these kind of different criteria that you list them, right? Like say there are different priorities, let's say, so that you can list them. A couple of related questions. Let me start with one. So let's say that this quest, do you do any check to see or that these are complete, or can they be incomplete, and would you discover them somehow?
Well, so the very honest answer is that we focused on what do I do if someone gives the priorities and the rules to me encoded already. We did not focus that much on who is giving them to me and how they are designed and where do these priorities come from. So that's
no, but just as you can, this is a curiosity question. So just as you can say that, okay, with these criteria, this is the least, or I shouldn't say least offensive, but least harmful path for me to take, right? Similarly, can you look at the criteria and can you not do some kind of check to see, hey, this is not, there are some holes in here. I'm wondering if you do any check to see whether there are holes in here, because it's a logically specified system, right?
Yeah. We do not do that check. We actually do not do that check. We just take it as like, this is our input and we work with that. So if there are some conflicts in specification, if the system is unrealizable or something like that, we will not figure that out. We will just give you the thing that is least violating, and it may be like completely violating everything that you wanted to achieve. It's just going to be least violating with respect to what we defined.
But it could be done, right? I mean, am I understanding this correctly? Because it's been some time since I did these things, but in other systems I do these, other kinds of logic formalism. So it should be possible, right?
It is possible with LTL as well.
Yes,
so for instance, Hadas Kresgazit has a very nice work in their tool LTL mob. If a user comes and gives a formula, the tool will answer to you whether this is unsatisfiable completely or whether it's unsatisfiable just in this environment.
So this related question to this is sort of coupling the first and second part. Sorry, I'm calling it first and second part, but two different aspects of your talk. Okay. So the related question is like, so if you had say if someone gives you this criteria and your system, because you're talking about sort of self-driving vehicles and so on, right? So are there additional safety protocols that will prevent it from doing something really bad? For instance, A, and B, like, when you have a human involved and you were talking about what is or is not considered a good thing to do, right? So do you have a sort of I know we've talked about this in other places, right? I'm just curious of more recent stuff, like whether there is a notion of what qualifies as being a good or not good, and whether you can learn from that to go back and change your specifications somehow. Is my question clear? Or was I rambling? Okay.
I will try to answer the way I understood the question. So you can definitely enforce hard constraints with this framework as well. The one thing that you need to do is basically treat some of the formulas as this is hard stuff, and then you can add the soft stuff on top of it. So things like you can never ever hit a pedestrian, no question. It can still be part of the framework. So yes, you can still have it on the motion planning level, you can have it on the control level, and the rest will still be working. Where these come from, yes, we need to ask, we basically need to ask people where these things come from. So so far our road rules, they come sort of from Vienna Convention. We did not translate the whole thing into LTL or STL. We did, yeah.
Now, the reason I didn't pose my question carefully then. So the reason I was asking this is you're also doing stuff where humans are evaluating and figuring out whether this is good or not good, right? So I was wondering whether you can learn something from it, because you talked about somewhat, you alluded to that, right? Can you learn something from it that will help you revise these things over time?
That's what we are hoping for sure.
Okay.
Yeah.
Okay.
Yeah, that's the idea. That yeah, precisely. That's the idea.
Okay. Anyone else? What? No questions. I have some, but
I have more.
I can't. So I know somebody's speaking. I can't hear her. Oh, sorry, I can't hear them. Sorry, Iran, go ahead. Yeah.
No worries. I would have waited if someone else asked. I don't want to just dominate that question. But my second question is a bit of a boring one. The answer would be I could have looked at your paper, but I will ask you since you're here. So you had two mention of Multirobot paper. One was mobility in demand, and the other one, the things that it was in the last slide. And I'm doing Multirobot. So I was Multirobot planning. My question basically is three things. A is, does your Multirobot planning using, I guess, these types of method, the robot has different goals? Do they have other constraints than avoiding each other? I mean, not collision. And most importantly, should be synchronized or not? I mean, is it like, what I mean by synchronization?
Yeah. The answer is it depends. We have different kind of setups on these kind of things. So in the mobility on demand, they are not synchronized step by step, but they do some centralized planning. So when I have vehicles going on the street, and then there is this obstacle and there is this critical zone that they cannot enter at the same time, what we do is we take the two leading vehicles, do joint planning in their joint space for them together, and then we let the rest follow. So that's how we approach this. Of course, this is okay for two leading vehicles, but we cannot do this for everyone in the road there. It doesn't scale.
Absolutely.
So that's centralized in that sense. What was
The
that was
last
the
one, it
second?
was the one, the paper you didn't mention. You said that, okay, I didn't want, I wish I was one to talk.
Yeah, the multi-agent stuff. So that's mostly my student's Georg's work. He was what he's trying to do is robots that have individual LTL specifications but dependencies between them. So something like I want to go there, 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 and there, but when I'm there, I actually need help from another robot because there is something heavy there and I cannot lift it by myself. So there's this scarce need for some kind of collaboration in the LTL formulas. They're sort of, every one of them has their own task to do, but the formula in theory is over the alphabet of all the agents. And then we are looking at what else we can do than just basically plan for everyone in a centralized way. So we are looking into exchanging what the others need to do to help you out through these assumptions, or you can even view it as auctioning because you can ask back and forth and so on. So he's looking into imposing assumptions on the individual agents, safety assumptions and fairness assumptions that turned out to be enough to assure that the formulas hold for all of them, if everyone is going to obey by them. Yeah.
Thank you so much.
Sure.
Martin, go.
Yes. So my question is regarding the autonomous vehicles. And I was wondering, I think in most cases where you actually have an autonomous vehicle that wants to drive somewhere, it doesn't actually know the entire world space. So this previous planning of complete paths is not really possible. So I was wondering if you also explored how you could integrate the logic rules into like planning with partial information about the world.
Yeah. So we looked into how you can work with limited sensing radius. So you know what's around you only within your radius, and then you observe all the signs that actually activate your rules. So we work with that in that sense, but we do rely that what's in the limited sensing areas is sensed properly. Yeah. We haven't done anything on partial observability within the sensing range.
Okay, but basically because of the limited radius, the car could go and sort of explore while obeying the rules.
Yes, precisely. That's what's happening. It's kind of like receding horizon going from yeah.
Okay, thank you.
Sure.
Okay, I have a follow-up question. Yeah. So, oh, by the way, how are you doing on time? Can you stay for a few more minutes, or do you have to go?
A few more minutes, like 5, 10 max. Yeah.
Okay.
But go ahead, please.
No, just one, right? I'm going back to this notion of this safety, right? Like, what does it mean for something to be safe? So I know you didn't get time to talk too much about it, but can you maybe briefly tell us, like, what the plan is? I'm still curious about the same thing, about how you're going to represent this and how you plan to maybe revise this over time, revise.
Yeah. So, safety, like the safety.
If it is safe for you to talk about safety, then please safely talk about it and tell us.
Yeah. So this is really tricky because I really don't know how this is where we are gonna go. from a formal methods perspective, safety has always been for me, you know, collision avoidance, or like always not something. That's what safety means. It's kind of like preventing something preventing a part of the state space, preventing entering a part of the state space. It's a complement to reachability. Mathematically, that's what it has always been to me. Now I started working with talking to social roboticists, and for them, safety is something completely different. It's more on the perceived safety end. And how we can encode perceived safety via these rigorous mechanisms, that's something we don't know and we try to figure out. We still don't know. So I'm not sure whether I'm answering your question. Mohan?
So I don't want to how to say, just put you on a spot on this one, right? Maybe I'll chat with you separately. It's okay. I'll stop here.
Definitely, we can do that. I would be happy to hear your thoughts. Yeah.
I'm just curious at this intersection of this definition and this learning thing process that goes on with it. I have some thoughts, but I will leave that for a separate conversation.
Sounds great.
Okay, thank you. And since you said you got to go, unless there is some pressing question, I will stop here and just on the record, for the record, thank you for making time to talk and give a presentation to our lab. And thanks very much. And hopefully we will have a chance to chat again sometime soon. Thank you.
Thank you so much. I sent into the chat my email address. Please do feel free to email me if you want to follow up and chat more. I will be happy to. Thank you everyone for listening.
You are an academic at a major institution. I don't think you can hide that easily. Your email will be known.
Okay.
But I will do a sort of round of applause for you.